Alright, welcome back, guys. In this video we're going to discuss how to divide radical expressions, and also how to rationalize the denominator when it comes to radical, and regular just simple radical term here versus something like this here where there's more expressions involved, variables and stuff. So let's get to it. So let's look at these two results here. We have the square root of 25 with 49. Inside the radical, we have a quotient. And over here, we have the quotient of two radicals. So it seems like we separate the radicals into radicals over radicals. So both methods there give us the same answer. So whether we chose to say, okay, I want to take the square root of 25 over 49, what would that be? Simply, we're looking for a fraction that square itself to give us 25 over 49, and that fraction is 5/7. Hence, the answer is 5/7. And suppose we want to split the apply the square root to both numerator and denominator, and see we still get the same answer. So that's what this second part is. If we split the fraction, we get square root of 25 is 5, and then square root of 49 is 7. So both get the same answer. So it turns out that similar with multiplication, we can apply the rule of radicals over a quotient, but there is a restriction, and it's very similar restriction to the multiplication. Both index must be the same in order for us to, whether we go from a quotient of radicals to one single radical over a quotient, or we start with a radical of a quotient to quotient of radicals, we must have the index matching there. All right, so we can go either back and forth or two forms. So we just did part A on the top there. Let's do part B. So this is saying that find the square root of 25 over y squared. We can either split the square roots like this here, and then that gives us 5 over absolute value y, or we can just say, okay, let's assume that the variables are positive. Let's just go ahead and keep it simple at 5 over y. So assume that y is positive. So we can do that, or we can say, let's see, what fraction, so that we square to get 25 over y squared. Well, that fraction is 5 over y. So we could have done that as well, right? So either way will work. All right, so let's look at this one. This one is a little harder because the radicand is not a perfect square fraction. So we want to apply the rule of radicals division and split this into a quotient of two radicals. So we have square root 16x to the third on top, divided by the square root of y to the 8th. When we do this simplifying of variables, we want to assume that all variables are positive, or the radicands cannot be negative. The radicands are a form of positive values. Okay, so how do we simplify this here? We can say on the top, we can use what we learned from the last section, simplify square root. 16 is 4 squared, so we can say that's 4. But then x to the third, we can have that as x squared and x. And the square root of x squared is going to be x. And then we can just leave one x inside. Over y to the 8, we can say that is y to the 4th, right? Because y to the 8 is y to the 4th squared. Right, and that becomes just y to the 4th. So yeah, so this is the answer. Let's do the cube root. Cube root, we can do the same thing. Cube root of 27, y to the 14. Cube root of ax to the third, and then we get 3 on the numerator for cube root of 27. Y to the 14, we can use a shortcut. We can say 3 going to 14 is 4 times remainder is 2, so that's y squared inside. Down here we have 2x. right, so that's the simplifying answer. Sometimes square root each numerator denominator takes a little longer. It turns out that if we combine it to a single radical, we can simplify it faster. So that's 16, and that's 4, because 80 over 5 is 16. Okay. Same thing here as well. Cube root of 16 and cube root of 4. Cube root 4 does not simplify. Cube root 16 is 8 cube root 2, but if we actually do this, and then we can simplify much faster because both indexes are the same, we can say that's the cube root of 4, and that's the answer. Okay. We could do this one as well. Index matching. Let's combine that into a single fraction. And then 3b. And then the b cancel. Then 3 go into 18 as well. So what do we get? We get 6. And then a to the 9. B to the 4th. Right? And I think that can be simplified further. So we say there are 4 divided into 9 is 2. So a squared comes out. And then 1a left behind. And then b, 4b, 1b come out as well. So that's just 6a inside. Okay. Alright, so moving on to rationalize denominator. Okay. Anytime we have a radicals in the denominator, we want to rationalize that, and the process rationalizing is taking this form here, and then rewrite that, into an equivalent form where we don't have a radical in the denominator. So this is like saying that taking, or actually, just rationalize denominator makes the denominator does not contain radical. Okay. So back in the day when there's no calculator to estimate, when you divide something like this, 1 over square root 2, when you set up the division, there's no calculator really do the long division back in the day, so you would have to estimate this, and it's harder to do this long division because this is an irrational number, so the decimal doesn't really terminate or repeat, so we can't really move the decimal over because we don't know when it ends. So it's hard to do this long division. So a rationalized denominator make it where you take this form and then you turn to the square root 2 over 2, and then this form is easier to do long division, right? So that's one of the many use for it. Now we still use this because it's a good algebra concept of manipulation, taking one form turn to a new equivalent form, and it's good for critical thinking. All right. So let's get to it. Okay. So I wanna make this square root 3. I wanna make the radical goes away. Okay. I want radical 3 goes away, meaning turn radical 3 into 3. Right. So the word how we do that is turn the denominator into something that can be perfectly square root. Okay, so if something perfectly square root, well, if we have the square root of 3 to make this into perfect square root, we need another square root of 3, right? So that gives us square root of 9, and this is square root of 24. So that's 3 in the denominator, square root of 24. We can look at that and said that's 4 times 6, and that's 2 root 6 over 3, and there's our answer. Oh. All right, so the reason why we times it by another square root of 3 because we have a square root. If it was cube root, we may need to redo it, include more than one factor like this one here. This is cube root of 5 over 16. Okay, so first we say, all right, we can split the radical. Okay. All right. So in this case here, we got cube root 16. We want to make the cube root go away, so we want to turn the cube root 16 into 16, or well, we can say, all right, is there the next, it's become next perfect cube number. Okay, well, what is the factor we can times to the 16, so that way it becomes perfect cube. I can think of that as 64 because this is 4 times 4, so we need another 4, so we do cube root 4 there. So now that becomes cube root of 20 on the top, and then cube root of 64 in the denominator. That becomes 4, right? 20 doesn't have a perfect cube, so we're going to leave it as cube root of 20. And so that's as far as we can go there, right? So the goal is just, trying to make the radical symbol goes away, and we have to make note of the index. Depends on the index, depends on the radicals. We want to figure out a way to times by a factor of 1, where the factor of 1 becomes, this thing where it makes the denominator turn into a perfect square or perfect cube number or a quad, if we have a quad, right? Let's do one with the variable. Okay. Here we have 4 square root of 5b. Another way you can look at this is multiplying inside the radical instead of splitting it. So what we can do here is we can say, all right, I'm going to go ahead and times something to the top and the bottom inside the radical. It doesn't change the answer. I want to make sure that when I times this, my denominator become a perfect square. So it looks like I'm missing just 5b, and then I'm going to turn that 5b as well. So if I do this, I get square root of 20b over 25b squared, and then we split that, and then 25b squared. Square root of 25b squared now become 5b, assuming the variables are positive. On the numerator, we can look at that and say, all right, 4 times 5, so that's 2 root 5b. Okay. So instead of splitting the radical like this, where they appear, you can actually times it inside the radical, and then, work your way around that and get the answer as well, right? So let's do one more. In this case here, we have a cube root of a over cube root of 25 b c to the 5th. Okay, so again, our goal is make the cube root radical goes away. Okay, all right, how do we do that? For the 25, we need another factor, so that way when we take the cube root of 25 times that number, it becomes a perfect cube. So from 25 to the next perfect cube, I can think of that as, one more 5, right? So that would be just a 5 there, because we get 125. All right, this is what we need here, so 1 more 5. And then for the b, we only have one factor of b. To get a perfectly cubed, we need 2 more factor of b. And then c, well, c to the 5th, the next perfect cube one that divides 3 evenly is c to the 6th, so we need 1 more factor of c. So 5b squared c. So now, our answer now is 3 cube root 5 ab squared c over, we have 5bc squared. And there's our answer. All right, hopefully that helps.